Hello and welcome to our presentation on our smart lock for our CIS427 project. For our smart lock, our group has decided to choose the CoAP network model. In the next slide, you will see the breakdown of the network model in terms of design, but for now, we will discuss why we chose CoAP as our model. First, CoAP is a one-to-one protocol, and the reason this is important for this specific project is because with the smart lock, security should be a top priority, and with a one-to-one communication, only the server and the client are communicating with each other. There are no other clients that will be allowed to communicate. This is a major difference from the MQTT model, which allows multiple clients to communicate with a said server due to it being a many-to-many protocol. This could be more efficient than CoAP due to allowing multiple clients to communicate, but it does make the server more vulnerable to attack by allowing multiple clients. Furthermore, with performance, CoAP uses less overall power than MQTT, especially when working with smaller packets of information. And since the only messages sent between client and server is a lock and unlock request, the data sent will be relatively small, making CoAP a better choice for less energy consumption. MQTT, on the other hand, would be better if the packet size were to increase. So if we were sending a lot of data between client and server, in other words. In continuation, since CoAP is a UDP-based protocol, that means that it is not connection-based, so we do not have to wait for a connection to be established before the client is able to request a lock or unlock. And since we value responsiveness and an application of low delay, this is a great choice for a network model since the client does not have to wait for a connection to be established. And in addition to this, we can ensure low latency with a CoAP model since it does not implement acknowledgements or retransmissions. This is something mostly done with TCP-based protocols such as MQTT. So since CoAP does not have these features, we can ensure that the latency is low since it will just shoot and forget. This might make communication not as reliable, but it will definitely make communication between client and server much quicker, which is what we are aiming for. So these are the overall reasons as to why we chose to use the CoAP network model over the MQTT network model.
For our design, we tried to keep it as simple and effective as possible. So we can see that we have three main parts for the lock. First, we have the client, which is just the mobile browser. Um, we have the gateway, which acts as a middleman, and then we have the actual lock, which will be running on a Raspberry Pi virtual machine. Um, we have very basic essential functions between these three parts. So first of all, between the mobile and the gateway, so the mobile, which is the user, would want to send the command plus the password, and then in return, the gateway would return the status code showing if whatever the user wanted to do is successful or not. Then we have the relationship between the gateway and the lock. So the gateway, first of all, whatever happens, anything that goes through it, it always stores logs. So be it from either the client or whatever it does to the Raspberry Pi, it always has logs stored, which the user can request to see whenever they want to with the correct password. And then, so between the log and the gateway, when the gateway receives a lock unlock command with the correct password from the client, it will forward that command to the Raspberry Pi lock. Um, and the Raspberry Pi lock in return would just lock or unlock. As for checking whether the lock has been broken or not, we can see that to make it as efficient as we can, instead of having to add, for example, maybe another observer node that's connected to the gateway and lock or something like that, the lock would observe itself to see whether it has been locked or unlocked as expected or not. So for example, if the lock is unlocked or locked, but what the command the credentials or the IP doesn't match what's stored in the logs as the last command, then it would send a notification that it has been broken, and that in turn would go to the user. So we could see how we made it simple and as efficient as possible to keep the connection and all the messages sent as clean and as fast as possible. For our requirements, and specifically our functional requirements, we have a few very essential requirements that enhance the user experience. So first of all, we have of course, the lock and unlock on demand requirement. So whenever the user wants to unlock, given the correct credentials, they should be able to do so. Um, there should be no problem in locking or unlocking whenever they want to. Then we have a one-use password. So in case of an emergency, in case of they forgot their own password and they have to lock or unlock, um, anything like that, the user will know a one-use password that they could use to also lock and unlock, which is kind of a temporary password. And then of course we have the permanent password, in which the user has a hard-coded stored password in the gateway that would allow them to lock or unlock or view the logs whenever they want to. Then of course we have the lock break notifications, which that's for security and any unauthorized access, or if the lock is broken, which means there was no heartbeat response. In our case, the lock would observe itself and the last command. If they don't match, then that's no heartbeat for us. The user would be notified if anything like that happened. We have the success or error messages. So if whenever the user uses the mobile browser to send commands, they will see whenever they send a command, they will see that they will get in response a code which is 01 or whatever that shows that it was either successful or the command failed. And as for the UI, um, the user wants something at least usable. We don't want to make it too complicated. We don't want to make the success or messages very hard to find or read on the page. It's very simple. And for the output log, all activity should be in a log file, which the user can request whenever they want to, and that log file will be generated by the gateway.
So for our non-functional requirements, we have chosen security, usability, latency, reliability, and responsiveness. Security should be the top priority for the smart lock, and as we can see in the description, it is the most important requirement. And the point of security is to not allow any unauthorized attempts on sending commands to the lock. Second, we have usability. Although we want our app to be secure, we also want the user to be able to understand how to use it. So we are aiming towards making it user-friendly by making a simple user interface so almost anyone can be able to use it. Third, we have latency. The program must receive and execute commands given by the client in a reasonable amount of time. And again, this is something that can be accomplished with CoAP, as it is relatively quicker in sending messages as there are no acknowledgements or retransmissions. Also, CoAP being non-connection based can help lower the delay/latency as well, since the user will not have to wait for a connection to be established. Fourth, we have reliability. A user should always rely on the lock to provide the security they need, and we plan to accomplish this by implementing a broken lock checker so the client can always see if there is suspicious activity being done. Last, we have responsiveness. We want the user to know if the commands they enter are being successfully executed or are failing. So with this, whenever a user enters a command, they should see a message letting them know the status of their command. So if they were to enter lock, they should see a message that says lock successful, something like that. or if they enter unlock, it should say unlock successful. In the next slide, we will see some performance measurements, which include some of our non-functional requirements. So here are some of our performance measurements. For the HTTP gateway, the latency between the gateway and the mobile client was 0.125 RTT. The overhead for the GET request was 407 bytes, while the response was only 107 bytes. The latency between the gateway and the CoAP server was 0.0026 RTT. And the overhead for the put request was 50 bytes, while the acknowledgement was 38 bytes. So for more performance measurements from the CoAP server to lock, the latency was 0.0026 RTT, the overhead being 60 bytes. And in terms of reliability, there were no lost packets at all. Some ways we have enhanced the security of our smart lock is first choosing CoAP. As mentioned in the second slide, CoAP is a one-to-one protocol, which means no other client can be in communication with the server at the same time as another client. We believe this enhances security since only one person can communicate with the server and no other malicious user will be able to communicate with the server while the client is. Our second feature in enhancing security is the randomly generated temporary / one-use passwords. These are the passwords required for a client to request a lock / unlock. And the only person who will know this randomly generated password is the authorized user. So no outside user will be able to know what this randomly generated password is. And even if a malicious user were to somehow manage to acquire this randomly generated password, since it is only a one-use password, it will be defective since the client has most likely used it already prior to the malicious user acquiring it. Our third feature in enhancing security is authorization. The client will first have to enter a password. This is different than the randomly generated one mentioned prior. In order for us to know if they are an authorized user or an anonymous user, if they are authorized, then they are provided with access to send lock and unlock requests with their newly received randomly generated password. This is a great feature as we can separate authorized from anonymous users. One way we can further enhance security with this feature though would be to also make the authorization password randomly generated as well. This way, it will be much harder for a malicious user to gain access to features and content that is only accessible by authorized users. Lastly, our last feature for enhancing security is a broken lock checker, which will be showcased in the demonstration soon. This broken lock checker will alert the user once an attempt or once the lock has been broken itself by a malicious user. This is a great feature for enhancing security since we can keep track of suspicious activity done by anonymous or malicious clients. This feature is also capable of being enhanced further by shutting down communication with the server after an attempt has been done to break the lock. So now that we have discussed the design, the reasons why we chose CoAP, and the measurements, as well as the functional and non-functional requirements, Ryan will now show you guys a demonstration of the project.
Okay, so this is our implementation for the smart lock. So our smart lock is broken up into three specific sections here. So the first one we're looking at is the gateway, which we're using a simple HTTP server with. So here we have the HTTP server. Here's just some simple variables. These are for the host and ports for the co-op clients it uses to communicate with the smart lock. Here are the paths to the resources on the server. And since we have those there, I will then show you the server here, which is right here. So here's our server. It has multiple resources. So it has a lock, which is the lock. So it will have either a locked or unlocked mode. And here's the other resource, which is the gateway resource. This is only changed from the gateway, and it will have the same status as the lock when it is changed. And this is used as a safety measure to tell if the lock has been broken. So I'll explain that once we get to the actual lock itself. So if we go back to the server here, pretty self-explanatory on a HTTP request handler. So if it's got a lock or unlock status in the URI or a view log, it will pass through checking for a correct URI, and then it will check for the correct hard-coded password here. If not, sends 401 errors. If it passes through with a correct URI and a correct password, it will then create a temp password here, so a system PW. This is done by the getPW function, which is down here, which it will then just create a password from lowercase letters, uppercase letters, and digits of a size 8, and it'll create a random implementation of those. And this password, since it's in the request handler, it gets reset every time, so there's no need to suspend the password, so it resets every time a new request is sent through. So there's no way of having the temp password being used an old one. So here is if a URI was a lock. So if someone wants to lock the lock here, it will then update the gateway value first to locked. Then it will update the client status here. So it'll update the client lock over here to a locked status. Then it modifies the status file that is indicated on the server, on the gateway server, just so people know if the lock is locked or unlocked at the time after a lock or unlock request has gone through. So here is the response from the client for an unlocked request, and notice that the unlock and lock both use the temp PW. Here, so same thing again, updates the gateway value, then it will update the lock value. And if none of those paths are correct, it just will send a 404 error with an incorrect path. If it makes it through, it will then append the log that is on the gateway server itself. So right here with lock or unlock requests or a view log request. It will do that, and this is the append log function, and here's just the server being set up. It's on port 8000 just due to the fact that 8080 is kind of a printer port, so you can't really connect to that on my local network due to it'll try to connect to the printer instead. Alright, so if we go to the server here, this is the co-op server. It is got the two resources, so the lock and the gateway resource here, and they're just simple with a payload of a locked and a payload of locked, and pretty simple co-op server. And then here is the smart lock itself. So we will run the smart lock here. It is currently locked. And this is the smart lock itself. So it will have two clients here, and it's constantly observing the lock itself, so it knows the status. So this is the lock, so it's constantly connecting with the co-op server to know if it has a lock or unlock request. And this is a simple check with the gateway, so if the lock changes from lock to unlock, it will then get the gateway resource from the server. And if the gateway resource does not match the lock resource, so say the lock is in an unlocked position and the gateway says it should be locked, it will then print the error saying the lock has been broken. So if we do that, we know that, and that will print the error. We tried to have the error actually send an email through an SMTP server to Gmail, through a Gmail, but that was too difficult to do due to the fact that Google's like kind of clamped down on Gmail being scripts using like simple SMTP to send emails. So Google's clamped down on that, so we weren't able to actually implement that. So we will now test the lock here using the my mobile device here on the Wi-Fi network, and we will try to unlock the lock. So if we do an unlock request, boom. This is just the thing checking the status because it moved to an unlocked position. But here is the unlocked lock. So I'll show it here. So it's a message ID of 697. So right here. So this is it getting the update from the CoApp server that is running on my actual desktop, and just for reasons, and the lock here is running as on the Raspberry Pi VM. So here it is telling it to, here is the thing telling it to be an unlocked right here. And here is the HTTP traffic telling it to unlock with the said password on here. And if we choose to lock the lock again, it will then update the lock with a lock request. So here we are. So you're in here with the locked request. So the lock is now locked. Here is 698. So here is it updating it with a 698. And here is the HTTP request right here with the lock. So we will then show what happens if the lock moves to an unlocked state and it is a broken lock. So we'll do it here with a simple CoApp client here. So this will just move the lock to an unlocked position. So we do this, unlocked. So this lock moved to an unlocked state, and here we have our error message. The lock has been broken. So that just covers the simple design aspect of our lock and how it works. So there we go.